Okay, welcome class to Physics 390 class 26. This is on emission and absorption of radiation. We're going to be looking at the phenomena of absorption of radiation by atoms, stimulated emission of radiation by atoms, and spontaneous emission of radiation by atoms. And we'll be applying some of our previous work on time-dependent perturbation theory, just one result from that, to this. We'll also look at the relationships between those three types of interactions with atoms. And finally, we'll look at something called selection rules. So this is from chapters 11.2 and 11.3 of our textbook. So let's get started. Okay, so how do atoms undergo transitions between energy states? Well, they need to interact with the electromagnetic field because atoms are electrical. So here is an electromagnetic wave, okay, with a well-defined direction and well-defined polarization. And the interaction with that electromagnetic wave can cause a transition between atomic states in an atom via the electric dipole interaction, okay? So this is the interaction here. This is the energy, H prime. It's E naught cosine omega t, which would be the electric field strength here, since it's the electric dipole interaction. And then Q times Z would be the, for the charge which is being driven, for the electron which is being driven by the electromagnetic wave, Q times Z is the dipole element, or the electric dipole. So that's why it's called the electric dipole interaction. So it'd be minus the electric dipole QZ times the electric field strength would be equal to the interaction between the electric field and the electric dipole. Okay, so that's what we have here. Now we can write this, what we're interested in here for the purposes of calculating the probabilities is the matrix elements of this between two possible states of transition, say psi A and psi B in the atom. So H prime AB would be minus PD, where PD is the matrix Q times the matrix element of Z between psi A and psi B. That's called the electric dipole matrix element because it's Q times Z matrix element between A and B. So that's why it's the electric dipole matrix element. That times E naught cosine omega t would be the matrix element of H prime, okay? So, so our previous result, I mentioned just a bit ago that we would be using our previous results from time-dependent perturbation theory. So our previous result for sinusoidal perturbation applies here. The probability to go from a lower energy state A to a higher energy state B as a function of t was equal to the amplitude of the upper energy state B squared, which was given by this when we studied the sinusoidal perturbation in the time-dependent perturbation theory. So it would be the matrix element VAB squared over H bar squared times a sine squared term over an omega naught minus omega term, omega naught squared. So this is an oscillating probability. So there's an initial peak and then a point where there's no probability of transition, and then a good probability of transition, and then no probability, and then appreciable probability, and so forth, because of the sine squared term. And then the stronger the perturbation V, the stronger the probability of transition. And then the closer we get the driving frequency of the electromagnetic wave omega to the characteristic frequency of the transition, omega naught, the smaller this denominator will be, and the larger this probability will be, the larger the peak of the probability will be. Okay, so in this case, we have our VAB. So in the leading up to this analysis for the sinusoidal perturbation, our our energy was VAB cosine omega t. So here VAB would be minus PDE naught, just reading this off from this equation here. So inserting that into this equation, we have PA to B, the probability of going from the lower to the upper energy state as at time t would be plugging in minus PDE naught for VAB and squaring it. We get PDE naught over H bar quantity squared times this sine squared over omega and minus omega naught squared term. Okay. So that's our expression. Again, assuming that we have what we call coherent light, light with a definite direction, it's going in a definite direction, it has a definite polarization. And I say that because in a little bit, we're going to be looking at incoherent light, where there's a mixture of directions and a mixture of polarizations, which is generally, unless we have a laser to make such coherent light, we're usually dealing with at least to some close to incoherent light. Okay, so let's talk about absorption, stimulated emission, and spontaneous emission. So in the previous expression, if we move from the lower energy state A to the upper energy state B, we say the atom absorbs an energy H bar omega naught from the electromagnetic field, because it's going up in energy, so it must be absorbing energy from the electric and magnetic field that it's interacting with. And we usually call that H bar omega naught energy a photon, okay, a little packet of energy. So that's absorption. It turns out if we redo the same treatment, which we've been talking about from A to B, to go from the higher energy state B to the lower energy state A, we actually, really interestingly, we get the same result. And this is called stimulated emission. So here's the same result. P from the upper energy state B to the lower energy state A is exactly the same expression as we had on the previous slide, okay? So that we had the same rate to go from the lower energy state to the upper energy state as we get from the higher energy state to the lower energy state in the presence of the electromagnetic wave. And this is called, this going from, in the presence of the electromagnetic wave, going from the higher energy state to the lower energy state is called stimulated emission. Here, the electromagnetic field gains H bar omega naught from the atom, because the atom is going from a higher energy state to a lower energy state. So it's giving off energy, which goes into the electromagnetic field that it's interacting with. In terms of photons, we have really one photon in and two coming out, which is kind of interesting. So we have this, it's easy to visualize this than is the easiest way to kind of get at it. So this first picture here is for absorption, which we talked about before, where we go from the lower to the higher energy state, and we have a photon coming in and driving that transition upward. Makes sense. For stimulated emission, we're still interacting with the electromagnetic field. So we have a photon coming in or around the atom, but that stimulates the atom to drop down. But that photon doesn't disappear because it's not absorbed. So that photon continues on, but there's another photon which comes from the transition downward. So we get one photon in because we have an electromagnetic wave around, and we get two photons out because we have the original one as well as the one that comes from the transition. So one photon in, two photons out for stimulated emission. Then there's spontaneous emission, as you can see here. And notice in spontaneous emission, we don't have any incoming photons. That's because we don't assume that there's an applied electric field in the form of an applied or directed electromagnetic wave. So we can have spontaneous emission without an applied electric field, that is a directed electromagnetic wave. And the reason for that is even without an applied wave around, there's still some electromagnetic energy present in the ground state of the quantum electromagnetic field, okay? So because it's quantum, the electromagnetic field is ultimately quantum, there's still a little bit of energy around, even when there's no directed wave passing through. Because of the uncertainty principle, we can't apply to the electric and magnetic fields. They can't both be zero. So there's still some little energy kicking around. And that's enough to stimulate a spontaneous emission event. So that's spontaneous emission. That's why atoms in the decay from excited states to lower energy states, even if we don't shine light directly on them, they will eventually decay because of this spontaneous emission process. Okay, so these results, which have, if you look again at this expression here, an oscillating transition probability, right? Sine squared of this oscillates in time, as we talked about just a minute ago, are for coherent light with a single direction and a single polarization. For the more common case of incoherent light, or have a mix of all directions and polarizations, it can be shown, and see the text for this because it's several pages of derivations, that instead of a oscillating transition probability, we get a constant transition probability. And it looks like this. The rate of transition from B to A, so this is from the upper to the lower energy state. So this would be for stimulated emission by incoherent light. Turns out to be this constant out in front, pi over 3 epsilon h bar squared, times the dipole matrix element squared, times rho of omega naught. Okay, and I'll explain what those are in just now. Now the dipole matrix element, which before was psi A Z psi B, because we had a definite polarization, a definite direction. Now the direction of the electromagnetic wave can be anywhere, so any direction in space. So we need to use R for which represents any direction in space for this matrix element PD, the electric dipole matrix element. And then rho of omega naught is the energy density. Okay, rho is density. So energy density per unit frequency in the electromagnetic field at a frequency of omega naught. So it basically tells you how much energy there is in the vicinity of the omega naught, which is the frequency of the transition from B to A. So the more energy there is in that in the field at that frequency, the greater the rate the transition will occur, which kind of makes sense. The more energy there is around at the right frequency to drive it, the faster it'll go. Okay, so let's talk about Einstein's interesting argument and how it connects to the lifetime of an isolated excited atom. So there's a famous argument by Einstein where he was able to find the spontaneous emission rate in terms of the stimulated emission rate for incoherent light. Okay, so that's what we were just looking at, the stimulated emission rate for incoherent light, where we had all the different directions and polarizations. So we assume, for his analysis, Einstein assumed a spontaneous emission rate A, a stimulated emission rate B, from B to A for the transition from higher to lower, times rho of omega naught. The rate is B times rho of omega naught, where B is pi over 3 epsilon naught h bar squared PD squared. So when combined together with the rho of omega naught, this is exactly what we had on the previous slide for the rate of stimulated emission for incoherent light. We're just separating out this B factor here for reasons we'll see in a second. And then we also have absorption, and that would be BAB for lower energy state little a to upper energy state little b times rho of omega naught. So the same form as the stimulated emission. And it turns out that BAB is equal to BBA. Again, we have this symmetry between stimulated emission and absorption, that they occur at the same rate in the presence of a radiation. Okay, so what Einstein did was he assumed that we had populations NA and NB, population NA of atoms in the lower energy state and a population NB of atoms in the upper energy state. And he looked and saw what could cause NB, the excited state population, to change. So that's dNB dt. What could cause that NB to change? Well, there's three things. There's spontaneous emission. The B state could spontaneously emit and go down to the A state. There could be stimulated emission. So the field around could drive the transition from B down to A, and we would lose an atom in B. And then we could gain an atom in B if the field absorbed, if a atom in state A absorbed and went up to B. So that's what these three terms are here. We take the number of atoms. The first term is the number of atoms in state B times the rate at which spontaneous emission occurs. That will be the per unit time, the number of atoms which are lost from state B due to spontaneous emission. Similarly, this would be the number of atoms that are lost due to stimulated emission, because this is the stimulated emission rate, BBA rho omega naught. And this would be the number of atoms that are gained in NB because of a transition from NA up to NB, up to state B. Okay, so this would be our kind of a rate equation with all the ways that the population of the upper energy state could change. Okay, so in equilibrium, that's what Einstein was interested in. Once things have come to equilibrium and we have these two populations, NA and NB, once they've stopped changing, so NA and NB are basically not changing anymore. Doesn't mean that there's not any transitions happening. There's always spontaneous emission happening and stimulated and emission and absorption if there's fields around. But they're happening at the same rate. So we get the same amount going from NA to NB as going from NAB to NA. So their numbers remain constant, even though there's a flow of different atoms between them. Okay, so anyway, in equilibrium, dNB dt would be 0. And if we set this equal to 0, we can solve for rho of omega naught in terms of A, NA, and B, the two B coefficients. So this is just an algebra where we factor out these two terms, we do some manipulations, and we get rho of omega naught is equal to the spontaneous emission coefficient A over this denominator. Okay. All right, so big deal. So where is Einstein going with this? Well, it turns out using thermal physics, there's an expression in thermal physics called Planck's thermal radiation formula. And you can see the text for this, since this is not a thermal physics class. Didn't want to delve too deeply into this in this video, but rho of omega naught can be written using thermal physics in a very definite form, okay? And by comparing that definite form for rho of omega naught to this form here, it's possible, and there's also a thermal physics tells us in equilibrium what the ratio of Na to Nb should be based on their energy difference. So we get an expression for this as well. So we get an expression for rho of omega naught from thermal physics for Na over Nb. Then we can relate A, B, and the two B's. And after some manipulations, which you can see the text for, we get the spontaneous emission A in terms of the stimulated emission B from upper energy state to the lower energy state with this constant out in front. omega naught cubed h bar over pi squared c cubed. Okay, so if we plug back in the BBA, which we had up here, which involves the matrix element, the electric dipole matrix element, we get that the Einstein's final result, using this analysis he did, this famous argument, that the spontaneous emission rate A is omega naught cubed times the matrix element squared of the electric dipole moment for the two atomic levels involved in the spontaneous emission over this combination of constants here. Okay, so at the time, this was a really a brilliant argument. This was later confirmed by other methods by later theories, later developments in quantum mechanics called quantum field theory and quantum electrodynamics. But Einstein found it from a combination of these expressions for the stimulated emission rate for incoherent light and some thermal physics. He was able to come up with this, which is pretty cool. Okay, so we have that. So what does that mean in terms of the lifetime of an isolated excited atom? So by isolated, we mean there's no electromagnetic field around, no directed light wave to stimulate it or to be absorbed. So if it's going to decay, it's going to decay by spontaneous emission. And it's excited, so it is in an excited state. So in fact, it will decay by spontaneous emission. So if we have a large population of isolated atoms, they will decay with this rate A by spontaneous emission. Now, if we look at this, if we look back at this rate equation up here, and we neglect these terms because there's no field around, there's no energy density in the field, we have dNb dt is equal to minus nb times A. So that's the rate of change is proportional to the number of atoms left with a negative sign. So that's a decaying exponential. That's the differential equation indicating a decaying exponential. So we get exponential decay with a lifetime tau, which is equal to, it turns out, 1 over A. Okay. So the faster the rate, the greater the rate, the shorter the lifetime, the smaller the rate, the longer the lifetime. So they're inversely proportional. Now, another situation which usually happens actually is that atoms, there aren't just necessarily two states, B and A, but there might be an excited state that there are multiple lower energy states which it could decay to, because atoms have a lot of levels to them. So there might be like A1, A2, A3, all with lower energies than state B. And in this case, this formula tau equal 1 over A generalizes to tau equal 1 over A1, the rate A1, plus the rate A2, plus the rate A3, plus however many rates there are for all the decay modes down to lower energy states. So you can see that with the more rates we add up here in the denominator, the bigger the denominator will be, and the smaller the reciprocal will be, so the smaller the lifetime will be. So we have a shorter lifetime for with the more decay modes there are, because there's just more lower energy states that the atom could spontaneously emit a photon and decay down to. Okay, so let's talk just briefly about selection rules, which are important for understanding what can actually happen in atoms. So we talked a lot about this PD, this electric dipole matrix element, and it's figured into all of our equations for the rates of transitions. Well, it turns out that often this dipole matrix element is 0 between two states. And if it's 0, that would mean that all the rates that we've talked about would be 0. So that would mean the atomic transition associated with those two atomic levels would be forbidden because the rate would be 0. Okay. So for example, for the hydrogen atom, we have PD, the electric dipole matrix element, would be QR, matrix element between N prime L prime L prime N prime L prime M prime and NLM, because the quantum numbers for the hydrogen atom are N, L, and M. Okay, so it turns out that by some analyzing the symmetries of the hydrogen NLM states, when you take the matrix element of R with them, that there are certain, you can come up with certain what are called selection rules, that PD equals 0. So this matrix element, which involves an integral, when you actually do it out, would be 0 unless the following hold. Delta L, which is the difference in L prime and L, is either plus or minus 1. So in the transition, L has to change by either plus or minus 1. And delta M can either be 0 or plus or minus 1. Okay. So that's somewhat restrictive. There's lots of transitions you can imagine that don't meet those requirements, lots of different pairs of atomic states that do not fit these selection rules. So indeed, many transitions are forbidden through the electric dipole mechanism. So let's visualize this. So here's a chart of allowed transitions for the first 4 N's and the associated L's. So for N equal 2, for example, we have L, it goes from 0 or 1, because it goes from L goes from 0 to N minus 1. So let's look at a particular case and look at the allowed transitions. So we have, let's look at N equal 4, L equal 1. So we know it has to decay, it has to go down in energy. So it has to go down from N equal 4 to either 3, 2, or 1. And the L has to change by plus or minus 1. So it can either go to N equal 3, L equal 2, so L increases by 1, or N equal 3, L equals 0, L decreases by 1. Or it can go to L equal, N equal 2, L equals 0, jump down 2 N's, but L still changes by 1, so that's okay. It could go to N equal 2, L equal 2, but that doesn't exist, right? Because N only has 2 L values. And then it could go down to N equal 1, L equals 0, because delta L then would be -1, which is allowed. Okay, so that's one with lots of different decay modes. This state has plenty of places to go. This N equal 4, L equal 3 over here has only one place to go, because since it's L equal 3, it has to go to an L equal 2, and the only energy level that has an L equal 2, which is below N equal 4, is L equal 3. So there's only one transition it can make. Okay, so it will take longer to do that, to decay spontaneously than this state would take, because this state has many different routes it can take. Notice, very, very kind of interesting, the 2s state. So this N equal 2, L equals 0 state right here. It appears to have no decay modes. Notice it's the only state here that has no arrows, well, besides the ground state. It's the only excited state that has no arrows coming out of it. And that's because it has to go downwards. It can't go down from N equal 2, L equals 0 down to this, because that would be L equals 0. L has to change. So it could go to N equal 1, L equal 1, but that's not an allowed state. N equal 1 only has L equal 0. So there's no state that N equal 2, L equals 0 can decay to that fits the selection rules. So does it decay at all? It actually does decay, but much more slowly via different mechanisms. Either a collision with another atom, where this energy can be dissipated in the kinetic energy of the atom it collides with, or via electric, not dipole, but quadrupole moment interactions, which are a different form of interaction. But it takes, generally those rates of both of those are going to be much slower than the electric dipole. So this state, the 2s state, is going to have a longer lifetime, significantly longer lifetime than the other states shown here, the other excited states shown here. Okay, so just to summarize briefly, we've looked at atomic transitions and radiation and energy levels in atoms. We've looked at spontaneous emission, stimulated emission, and absorption. We've related those three together through Einstein's argument involving the expression for stimulated emission with incoherent light and some thermal physics, and gotten a really nice formula for the spontaneous emission rate. We've related that to the lifetime tau, and we've seen of an isolated atom in an excited state. And we have seen that while the electric dipole transition does cause transitions, not every transition is allowed. If this dipole matrix element is 0, which it often is, that transition is forbidden. It doesn't happen. We've looked at some specific examples in the hydrogen atom there. Okay, so I hope this has given you some insight into atomic transitions and the interaction of radiation with atoms. Thank you for your attention, and I will see you in class.